Welcome to the E-Pathshala lecture series on computer science. We are in the 15th module of the course Computer Graphics and Visualization. So, in this module we will be learning about the viewing transformation, and followed by that we have projection transformations, which are important parts of the 3D viewing. Actually 3D viewing completes with the viewing transformation and projection transformation. So, in this module we will focus on viewing transformation. Okay. In the previous module we have concentrated on 3D transformations and the coordinate systems, and that we considered the conventions. All that should be remembered, because whatever lecture follows will have a lot of references to those conventions. Okay. So, let us look into what is 3D viewing. Okay. Let us this course, the contributors for this course are these people mentioned here. The objectives that we have for today's session, in this session, is how do we set up a coordinate system in 3D, and setting up that coordinate system is actually the viewing coordinate system. We call that a viewing coordinate system because in 3D we have a complete, all the 3 dimensions are there, and we need to identify a location, a position, that is a position, an orientation, a kind of the set of objects that are required to be captured, and so on. So, 3D goes much more complex than the 2D, and before we get into how do we capture 3D scenes, we need to understand how a 3D viewing coordinate system is set up. We call that the name viewing coordinate system is because it is from that reference position we will be viewing the world. Okay. It is something like, imagine you are holding a camera, you are standing on a vantage point, you have chosen the direction, orientation, position and everything, and then now you are taking you are capturing the world. It is similar to that. So, in 3D viewing we are imagining a position, direction and orientation for looking at the 3D world. That is the basis here. So, followed by that is to understand the taxonomy and types of projections, that involves projection transformation, which are parallel and perspective, which are very important in this series. Okay, let us focus on the how viewing coordinate system is set up. What is 3D viewing? 3D viewing is basically setting up the viewing coordinate system and then setting up the projection like parallel or perspective. So, that is simply understood as 3D viewing. At the end, if you see, we have the clipping transformation and viewport transformation follows the projection transformation. So, first we assume that the world is made up of a lot of objects. Okay. Each of these objects has got its own size, its own what is called volume, or its own parameters or dimensions. For example, consider you have to create a 3D object, okay, like a sphere. So, first what we would do is, you can imagine any 3D modeling software like 3D Studio Max or Maya or Blender, like open source software. Or you can just pick an object and simply you take a position, that is you pick a sphere like object or the standard object, then you change some parameters for the object like radius, like size basically for the sphere, that is what you would do, and position it appropriately and maybe orient it and so on. This is all done in the modeling transformation. The next step is the viewing transformation. So, imagine we are setting up a viewing coordinate system, and now how do we look at the world from these coordinates, because the world looks different from different viewing positions. So, that is an important observation. So, we call changes from there is transformations, that is conversion from world coordinates, the modeling coordinates to world coordinates is the viewing transformation, and the viewing coordinates to projection viewing transformation to projection transformation, we get the viewing coordinates, and projection coordinates are what we get as output of projection transformation, and clipping transformation is the next step that is done. So, what is projection in between is that when we imagine a viewing position in space, the next step is to identify what part of the 3D world should be captured. So, that is defined by the projection transformation. So, projection transformation exactly determines what part of the 3D world is what we need to capture. So, that defines the volume. Okay. So then later we have to apply clipping on this transformed coordinates, that is remove all that is outside the volume that we have determined, that we have defined. So the step of projection transformation is to identify a view volume. Imagine you are holding a camera, that is you have defined a view volume. Volume is a kind of area, that is region, and this is the volume, say for example from here to say few meters is the volume, and whatever that falls within the volume should be viewed, and whatever that is beyond the volume should be discarded. So the step of clipping transformation here takes into account the removal of all those, that is basically consider what is inside the volume. So the projection transformation determines the volume, that is the view volume it is called, and the clipping transformation identifies what is inside the volume and what is outside the volume. Consider whatever is inside the volume, discard whatever is outside. So finally it is to be converted into a viewport, and viewport to 2D. So 3D proceeds till the point in time when we convert to viewport, and from viewport to device it is again 2D. So we get a feel of 3D, but at the end it is 2D again, only the perspective changes here. Okay. So all the steps from modeling to viewport are all done in 3-dimensional coordinates. Okay. In 3D operations are performed. Okay. So as you can see here, the modeling transformation includes creating each object separately in its own coordinate system called the local coordinate system, or the local coordinates, or the model coordinates as you can call. Now take all these into another reference position in space called the world coordinates, and then the world coordinates are assumed by the various objects. That is what you are seeing here. Now how to set up the viewing transformation here, that is the crux of this discussion in this module. Viewing transformation is nothing but fixing a position in space and then identifying the direction for that for view, and identifying the orientation for the view. Okay. Orientation for the view is like how, imagine you are holding a camera, and how do you position it? Positioning it is the origin of the camera. Okay. Just first fix the camera, that is positioning. Then you rotate it, or maybe you tilt it. Okay. You can move it, or so the other two directions determine the orientation for the camera. Okay. So position, the other 3 directions for that sake. Okay. This the origin is the position where the camera is actually fixed. So how do we do this is this is actually called the new coordinate system that is created finally at the end is called the viewing coordinate system. So that is the reference position for viewing the world. Okay. So for this we imagine a direction, a position P0 in the 3D world. We imagine a random position in the world coordinate system, and identify that as P0, and whose coordinates are x0, y0 and z0. Now from that position we need to take out 3 mutually perpendicular directions, or we need to create 3 mutually perpendicular directions. And how we are going to do these 3 mutually how we are going to create these 3 mutually perpendicular directions from the crux of setting up the viewing transformation. So the first step is to consider a position in space called P0. Okay. P0 is the origin for the viewing coordinate system. Okay. The next step is to identify the z direction of the viewing coordinate system. Okay. How do we set up the z direction is, OpenGL has one way of doing. So other methods, there are many ways of identifying the z direction, and if you consider the OpenGL way of doing things, OpenGL talks about a concept called look at point. So that means imagine you are looking into the world, you are looking at a particular object, identify a position on that object. Okay, identify a position on that object, connect the origin, that is the position that you have chosen, which is P0, to that position on the object, that is your look at point, and you connect these two with a straight line, and you extend this infinitely. You extend this infinitely, that is the z direction of our viewing coordinate system. Okay, let me repeat this again. Consider a position, that is, imagine you are looking at a particular object in the 3D space. Here in the diagram it is shown as P. P is a point on some object. Okay. Now connect P with the P naught, and that direction forms the z direction of the viewing coordinate system. Now as I said, if we consider the right handed coordinate system, always the z direction is the positive z direction is represented by the middle finger pointing at the self. So imagine so your view is always along the negative z direction. So the direction from P naught to P is the negative z direction for the viewing coordinate system, and the direction from P to P naught is the positive z direction of the viewing coordinate system, which is identified as ZV in the diagram. So first the ZV direction, the positive z direction, which is the ZV, Z viewing, is obtained. Now the next step is to identify the remaining two directions, which is x and y. So our aim is to find three mutually perpendicular directions. How do we get the x and y? Now before we go to x, we will do y. Y is something like which is generally considered to be a direction which is perpendicular to the z direction, but because we are in a 3D world, we do not know, or we cannot exactly identify what direction can be the y direction. So we cannot exactly, because we are not still aware of our orientation. So we cannot readily identify the perpendicular direction y, which is exactly perpendicular to z and x, because now x is not known, the y cannot be perfectly identified. Let me repeat this again, the y direction cannot be perfectly identified because we are not still aware of x, and y direction is considered to be the direction that is perpendicular to x and z, and x is not known, so this y can be arbitrarily oriented. So to solve this problem, y and z you can interchange in the diagram. Simply a line that is parallel to the upward direction in the world coordinate system. So we get the y direction, but that is not correct. Now what do we do is, we consider a plane perpendicular to the positive z direction. We consider, we know the z direction very well, very perfectly. We have the z, we have got the z direction so perfect, which is the straight line ZV showing. Now imagine a plane, or identify a plane perpendicular to the z direction. Okay, already our y is something like this. Okay, but y is not exactly correct. What is that we do is, but we know very well that y should be in the plane which is perpendicular to the x direction. So what do we do is, we take a projection of this y direction onto the plane which is perpendicular to the z direction. Let me repeat, because y should be the direction which is exactly perpendicular to the x direction, and also should be within the plane containing the z and y, x and z, when the z direction is considered, it is the x and y plane. So what is that we do is, we will be projecting this direction onto the plane that is exactly perpendicular to the z direction. So when we project it, what happens is, now we get an assumed, a rough y direction, an approximate y direction. Still it is not correct. Then we take a direction that is perpendicular to the z and y. Once we have the y direction, which is a projected direction, and the z direction, the direction that is perpendicular to y and z will be the x direction. Okay, the direction that is perpendicular to the y and z is the x direction. So directions perpendicular to a plane can be easily obtained by considering two vectors within the plane and take the cross product of the plane. As you know from cross product function, when you take two directions within a plane, on the same plane, and when you fold your fingers from one direction to the other on the plane, that is the perpendicular direction is the direction normal to this, and which is our third mutually perpendicular direction. So that is how we do this. Let me repeat, the z direction is first formulated by identifying a lookout point, and the direction from P to P naught is the positive z direction for the viewing coordinate system. Now for the positive y direction of the viewing coordinate system, we simply imagine the direction that is parallel to the y direction, the upward direction of the viewing of the world coordinate system. Then we take a projection of the y onto the imaginary plane perpendicular to the z direction, and we take a cross product of the y and the z to get the correct x, and when we get the correct x, we can take cross product between x and z again to get the correct y. So that is how this viewing coordinate system is set up. The same thing is explained in the slide that you are seeing there. Choose any upward direction for y axis, and that is our y direction, and then again we take a cross product of the y and the z to get the correct x, and later to correct the y we can take the cross product of x and z to get the correct y. So, the unit vector along the x direction is considered as u, the unit vector along y is considered as v, the unit vector along z is considered as n. So, it is called u-v-n coordinate system. So, the cross product between v and n gives a direction which is the normalized u, and the cross product between n and u will get the v direction, which is finally the upward direction. Now, the viewing transformation here, how do we perform? So, once we have set up a coordinate system with 3 mutually perpendicular directions, that is called the viewing coordinate system. Now, we have got the world coordinate system. Now, how do we perform a translation between world to viewing? That means every object, now that because we are seeing from the objects from a different position, they would assume different dimensions. Obviously, their coordinates would be different. So, how do we perform a translation from world to viewing? So, the step is, as you can see here, the first step is to take the translate the origin of the viewing coordinate system such that it aligns with the world origin, as you can see here. The transformation is simply translation minus x naught minus y naught minus z naught. Simply translate the position p naught of the, which is the origin of the viewing coordinate system, such that it coincides with the origin of the world coordinate system. The next step is to perform rotations for this coordinate system, which is now aligned with the world origin, the origin of which is aligned with the world origin. Perform first rotation about x axis, so that your zv is brought onto the, our aim is to align the viewing z with the world z, viewing y with the world y, viewing x with the world x. So, now first we perform a rotation about x axis such that the z is in the z of the viewing coordinate system, the z axis of the viewing coordinate system is in the xz plane of the world coordinate system. So, the next step is to perform a rotation about the world y axis such that the viewing z axis now aligns with the world z axis. So, there is a they now once they align, the next step is to rotate about the z axis so that the y and x are perfectly aligned. So, it is a rotation about all the 3 coordinate systems are to be performed in succession, so that the viewing directions exactly align with the viewing coordinate system directions, exactly align with the world coordinate system directions. So, once this is considered as conversion from world, now you need to do the reverse translation. No, you are not doing that, because it is not the, it is conversion. Once the conversion is done, it is all over. Once you have the composite matrix ready, do not do the reverse transformation again here. It is not that, we are not doing the reverse transformation. So, our aim is to finally align the world coordinate system with the directions of the viewing coordinate system with the directions of the world coordinate system. Okay. So, for that we need to perform Rx, Ry and Rz in succession, and that is our composite matrix. That means, give any input as which is the world coordinate, world coordinates, apply this matrix, the composite matrix R on the world coordinates, you get the viewing coordinates. So, that is the essence of it. So, apply the world coordinates on this composite matrix, apply composite matrix on the world coordinates, you get the viewing coordinates. So, that is shown here in this slide in steps for 3 rotations. Now, the composite matrix R is given by the U1, U2, U3, 0, V1, V2, V3, 0 and N1, N2, N3, 0. The U, V, N are the unit vectors along the 3 mutually perpendicular directions, and these are the components of the unit vectors. U1, U2, U3 are the components of the unit vectors. Now, the final matrix from M, notation of final matrix from world coordinates to viewing coordinate conversion is given by a translation first that we did and the rotation, and it is given by R into T, and the matrix T is 1 0 0 minus x naught 0 1 0 minus y naught 0 0 1 minus z naught and 0 0 0 1. So, when we multiply these two, what we get is the matrix. Now, apply this matrix on any world coordinates, you get the viewing coordinates. So, it is an important thing here that you should remember. Now, after this viewing transformation is performed, the next step is to perform projection transformation. As I was telling, we start with modeling coordinates, modeling transformation, world coordinates, viewing coordinates, and then projection coordinates, and then we get the viewport coordinates, and finally to clipping coordinates to viewport and to device. So, in this sequence we are at the step where we need to perform projection transformations. That means once you have decided how to project from where to observe the world, the next step is to identify the view volume. Okay, you have identified position now, you have identified your orientation now. The next step is to identify the view volume. Identifying the view volume is done in projection transformations. Do not be under the assumption here that projection is conversion from 3D to 2D. No, not exactly. In 3D viewing, projection transformations simply convert data in 3D to data in 3D again. That means after conversion we get another 4 by 4 matrix. From one 4 by 4 matrix to another 4 by 4 matrix, the coordinates get converted. So, from viewing coordinates to projection coordinates, the data gets converted. So, projection transformation, the essence, the aim is to simply select the view volume, that is define the view volume, the shape of the volume. So, that is the purpose. And now projection transformations can be summarized in this taxonomy diagram. Always we assume that all our projections are being done on a projection plane which is a 2D plane. So, finally at the end we will be projecting, we will be displaying anything on a 2D plane. So, these projections are called planar projections. That is, if you project a 3D object onto a non-planar surface, then they become non-planar geometric projections. So, our assumption is planar geometric projections. So, we imagine a plane and the objects are being projected finally onto a 2D plane at the end. So, now the two fundamental classes of projection are parallel and perspective. So, parallel projections and perspective will go deep into each of these. Parallel projections are further classified as orthographic and oblique, and orthographic projections are further classified as top, front, side, axonometric projections, whereas oblique projections are classified as cabinet, cavalier and other. While the perspective projection transformations are there are three types, which are 1 point, 2 point and 3 point perspective projections. Let us understand first projections, and we will go further into how do we derive matrices for these transformations. So, what is parallel projection? Parallel projections are where an object is projected onto an imaginary 2D plane along lines which are parallel to each other. So, the idea is an object is projected along lines. So, imagine an object, it is projected along lines and these lines are parallel to each other and you are projecting it onto a flat 2D plane. This is called parallel projection. As you can see in the diagram, an object is projected onto a viewing plane. We call it viewing plane, you call it projection plane, you call it the plane of projection, in whatever manner you call, it is the final plane on which we would see the object. So, object projected using parallel projections is as shown in the first diagram. Okay. These lines are called lines of projection and these are parallel to each other. Now, this is perspective projection diagrams, and how perspective projection is, that is, an object is projected, this is the object, okay, this is the plane, this is the object finally seen on the plane. An object is projected along lines which converge at a point called the center of projection. So, the important difference here is parallel projection, the lines of projection are parallel to each other, so they do not converge at any point. Parallel lines do not meet anywhere, so they meet at infinity, as we know from the various theories. So, perspective projection, the lines of projection converge at a point called the center of projection. Now, the difference is that, as you can see, the size of the object getting smaller in perspective projections, while the size of the object remains similar in the parallel projections for the projected object. As you can see, a smaller object projected onto the view plane in perspective projection. So, our human eye is basically sees the world along perspective projection. So, our human eye has the vision which is natural, which sees the world along perspective projection. So, the advantage of parallel projections is there, and there is advantage of perspective projections. You can choose one of them for your application, and depending on the requirements you can choose either. So, parallel projection gives better views of the various sides of an object. So, for example, as mentioned before, we can get better views of the front, the sides, that is, I am seeing the world from the front. Say for example, there is a front view. If I want to see the world from top above, I will get the top view. If I want to see the world from side above, I will get a side view. So, parallel projections are used for having these views of the 3D world, the top, front and side. Whereas, perspective projections are meant for views which are human like more. For example, as you can see here, the object size is reduced, and at the center of projection the object is nullified. So, it looks like, so for example, distant objects, how do they appear? They appear like small dots. You see, if stand here and I look at a distant object, it appears as a dot. So, similarly, the size of the object reduces with distance in the perspective projections, and because of the center of projection or the point of convergence. And now, let us see the most important differences between the two parallel projections and perspective projections in this slide. The lines of projection are parallel to each other, and the lines of projection converge at a point called the center of projection. It is also called as projection reference point in other terminology. It is also called as I. So, I, center of projection or projection reference point. And the next difference you can notice, suitable for generating top, front and side views of a 3D scene. So, we generate these views, but with perspective projection we can generate perspective views. Orthographic projection is the default projection, and one point perspective is the default projection. We will learn about them later in the discussion in the next module. The view volume, very important, is that the view volume has got the shape of a rectangular parallelepiped. What is this rectangular parallelepiped? Is a box. Imagine a rectangular box. The shape of the view volume here in perspective projections is a frustum. Frustum is like our camera olden day, that is the frustum is something like it gets narrowed down or tapered ends and the broader front. So, like our panoramic cameras are initially the front it is wider and it gets narrowed down at the end. So, that is called the shape of a frustum. And another important difference is it preserves the relative proportions of the sides of an object, and it does not preserve the relative proportions of the sides of object. What does that mean is, when you project objects using parallel projections, the sides and the actual sides that you measure for the actual object and the projected object would be related, and whereas in perspective projections the sides of the object gets distorted. Okay. The center of projection is at infinity, as you know, parallel lines meet at infinity. The center of projection here is at a finite point, at a known point. And the last difference is, the views are less realistic in parallel projections, the views are more human-like look in perspective projections, so more realistic. Okay. That concludes this session, and this module talks about, as we have discussed, about viewing transformation and an introduction to projection transformations, which are parallel and perspective, the two fundamental classes of projections. And the references are the same, Hearn and Baker, Computer Graphics with OpenGL. Thanks for the